Okay, so you wrote, algorithms cannot be creative by definition. The human brain can be creative. Therefore, the human brain is not just algorithmic.
Yeah, this is the most important point, I think. I still stand by that. That's quite a good statement, actually.
Hey, everybody, welcome to Doom Debates. Today I've got a special guest, Professor Lee Cronin. In this episode, we're going to debate Lee's claims about the limits of AI capabilities and my claims about the risk of extinction from superintelligent AGI. It's what you come here for. So a little bit about Lee's background. He's the Regius Chair of Chemistry at the University of Glasgow. His research aims to understand how life might arise from non-living matter. He's developed innovative approaches to creating lifelike behaviors in chemical systems. And in 2017, he invented assembly theory as a way to measure the complexity of molecules and gain insight into the earliest evolution of life. So Lee, how is that? And whatever you want to say, try to elaborate on the arc of your research and your current passion.
Yeah, thanks for the intro. The intro is great. I am interested in understanding how life has come about through chemistry. It seems that chemistry is the paradigm which life has come through. But I think there's three big questions, I think. The origin of life, the origin of intelligence, and the origin of consciousness. And they all seem to be related. However, as a chemist, I can only do with the fan to cells part, or so I thought. But I'm interested in understanding how life is creative. I think that's quite important. And also the limits of explanation and explanatory theories. And that's why, I'm coming on to help you out about the notion of superintelligence, which Nick Bostrom coined. It's always great to coin a term that everyone grabs onto, but then when you actually question it, and we'll get to the limits of computation and mathematics on this. But anyway, I'll let you lead on that because I have very specific questions that turn into very specific experiments. And I think what I want to say is I'm an experimentalist and I believe in doing theory with experiments. And we can talk, but talk is cheap if it's not grounded in some kind of falsifiable framework, which is why I'm really happy to do this stuff, because the more I talk to people who have got interesting ideas, the more I can evolve my own ideas and then do new experiments and then either confirm or change the ideas. That's the process of science. I think it should be done more openly, with more humility, and also with a little bit of wonder, because I have no clue how the universe works.
Well, you certainly have my respect for coming on this podcast, because I do think that you and I are going to disagree on intelligence and doom. And we've engaged for one or two back and forths on Twitter. And most people will, they won't come on, or they'll even block me on Twitter. But you have done the absolutely respectable thing and come on to engage. So thank you for that.
Yeah, I mean, the tweets are fine, right? As long as people aren't snarky or, I think it's important to be willing to change your mind. And I hope you're willing to change your mind, or at least open up to the possibility of other things being happening, because I do think there's a very important thing to engage with culturally. I don't think it's acceptable for me to say you're simply wrong without explanation, or to make a statement about AGI, or AGE as I call it, anti-gravity happening suddenly and it's all floating away. We need to think about these problems in a reasonable way. So I think it's going to be a fun discussion. And if we agree, it would be really quite boring. Why would it come on?
Yeah, exactly, right? That's the spirit.
Enjoy the Cronin Club. I mean, I think that the most important conversations must be about why we disagreed. So what I'd like to get out of this is really interesting points of disagreement where I can go away and do my homework.
Great. I think it might actually be interesting to start from your worldview, and in particular, assembly theory. I can't say I'm an expert on it, but I've listened to a couple of podcasts where you attempt to explain it to a lay audience. So maybe give us a really quick shot at, my audience isn't exactly a lay audience. We tend to be familiar with AI concepts and computer science a little bit more than average, but maybe take a quick stab at just giving us the high-level overview of assembly theory.
Yeah, sure. I mean, there's actually a paper we published last year in Nature that's open access. It's not, although all the discipline experts went crazy and said it's a horribly written paper, actually all the non-disciplinary experts, the non-dogmatists, were able to read it and understand it just fine. And so I can point in that direction. And also, if like sounds like it's in nature to be complicated, it's not. All assembly theory does is says, hey, there's this thing called causation that seems to be present in our universe. And it appears that causation can act from the bottom up, from the atoms all the way up. So that's the first thing, right? So that's one side. This is this concept of causation. If you're a mathematician or a computer scientist and a philosopher, you might subscribe to the Bertrand Russell view when he says, causation is like the monarchy. It looks nice, but it has no use. And that phrase always was kind of like, wow, as a chemist, I only work in the causal universe. Reactions start, reactions end, reactions end, things live, things die, there's a beginning, there's an end. So what assembly theory does, and let's go back to the question, right? Because I'm interested in questions. It's like, how complicated does a molecule need to be? Like, how many different parts does a molecule need to be for me to conclude, if I detect it in an amount that I can count, an abundance, that it was made by some process which required an act of causation, if you like not just a random maelstrom of atoms coming together somewhere, like actively a process, be it genetic or technological, or in a when I mean genetic and something in a cell, because the only processes I know that right now that are causal in the universe with information, and that's a very loaded term, we should go there, seem to be from living systems or the consequences of living systems, like a factory that can build something. So a really simple question. Hey, I found this complicated molecule. Where did it come from? I've detected 1,000 identical copies, and there's too many parts for it to come together in that quantity. That was the start. Faced with this thing, I went, right, let me have a look at the molecule. Can I deconstruct the molecule? And I realized that I could deconstruct the molecule on a graph, keeping the causal components on the graph, and say, no, you can't just have access to the causal components unless there's some ordering. And what assembly theory allows you to do is basically break down any given object mathematically precisely and order the parts causally using recursion. And that's really quite nice because I haven't been able to really explain this to a computer science audience satisfactorily until actually last few days, where the collaborator we worked out and said, why is it not Kolmogorov? And the reason it's not Kolmogorov, it has called a proper ordering, which is related to the physical reality, the bonds, where Kolmogorov has arbitrary ordering depending on the language in which you're working. So that's kind of cool, right? It's something I want to be engaged with computer scientists on because it's quite interesting, because the assembly index looks like it's looking at compression. It's not quite that. It says the assembly index. So then you have this thing in assembly queue says, hey, I can now predict if your object has more than X parts, that it must have been created. Now, that is a really loaded phrase. You think you have problems talking to people who think doom, it doesn't exist. Think about talking to creationists who want to then say that these things are created. So that's the kind of start of assembly theory. I can carry on and then let it pause there, let you come back.
Great. Lots to unpack there. I want to go back to when you said you can't have access to the causality. There's some ordering. It made me think, Judea Pearl says you can infer causality from statistical relationships. Are you familiar with that? And how does that relate to assembly theory?
I know Judea's work really well. Judea's work is really about kind of understanding causation from a different perspective using statistical approaches. And that's really quite nice. It's more consistent with how we deal with things in our reality in StatMech, but it doesn't give a causal mechanism, okay? It gives you something else. It allows you to take the information. And I'm actually working on some comparisons with Judea Pearl's work. Now, Judea Pearl's work tries to solve different problems. It's not better or worse. It's just different. But Judea is quite a genius that he's realized that causation is important in the universe, and you can infer evidence of causation statistically. And from that point of view, I very much agree. But technically, he has done some very interesting things that are way above my conceptual capabilities, I would say. And so I don't want to be able to kind of talk about his work with authority.
Right,
I'd
right,
love
right.
to talk to him about his work and understand it. But they are different, and there is like a statistical inference rather than a mechanistic and build it.
Okay, great. Let's take an example because you mentioned that you can use assembly theory to analyze a particular molecule's assembly index, and then you can also generalize it to analyzing other systems, like maybe a biological organism, maybe even a software system. Can we just do an example that's just like a robust, simple example to just illustrate how assembly theory can analyze something?
Yeah, I mean, if you take the molecule, so if you take you take the drug Viagra, or you take the drug, or you take the natural product Taxol. Taxol is a natural product that's found in the Pacific yew tree. It has about 69 bonds and about 70 odd heavy atoms, and it is quite a complicated natural product with 47 carbons and a nitrogen atom and 14 oxygens, I think. I don't know. I should know the formula off by heart. But it's a complicated, what we call secondary metabolite. And it is made the consequence of the genes present in this bark, right? So in all the cells that compose the surface of this tree, it's a secondary metabolite which forms. What is the purpose of Taxol? Well, probably it's a signaling molecule or a toxin for fungus or things that grow on the tree, and they just stop it from growing. It also happens to be a very good anti-cancer drug. If you can make it in high enough quantities, you can use it to prevent vascularization of tumors. And chemists this molecule a lot because it's one of the hardest molecules to make, and many years and many efforts of people trying to make a semi-synthetic route and then a synthetic route to Taxol, because you're literally talking about probably 100 chemical steps. I think they've compressed it now down to 50 or 60, but this is a hard molecule to make. Lots of parameters, concentrations, temperatures, recipes, purifications. So making this molecule is a feat of engineering akin to somebody building a very, intricate sports car, right? By engineering standards, if you like.
Right. Okay, so what does assembly theory tell us?
So if you take Taxol, you decompose it, the assembly index of Taxol is 23. And that is a very large number compared to what you can get randomly. The threshold we find for organic molecules on Earth, when we basically survey random gamishas that we make in the lab and look in the environment, you struggle to get anything that has an assembly index above 12. And every number that the assembly index goes up, the space is at least double exponential. So that the space through 12 to 23 is a universe or more of combinatorial space. It is truly ginormous.
So what is it about Taxol that pushed the assembly number above 12?
So the Taxol is very unsymmetrical. So when you cut it up, the parts, you don't get reuse easily. There's lots of, unique twists in the molecule. And so there's not that many repeat units. It's really unique. So despite you could have had a maximum assembly index of actually 68, because the maximum assembly index for a molecule is n-1, where n is the number of bonds. So you had maximum difference, it would have been 68, but actually nature still compressed it down to 23, which is quite good. But 23, which means there's still some reuse in that molecule. There's just 23 irreducible parts, if you like.
Okay, now, and I see why you compared it to Kolmogorov complexity, because it's kind of like looking how complex or incompressible a particular design is. But I think that if I understand correctly, the difference is it's not just about the information represented by the molecule, but it's also about the process that made the molecule.
I think that's absolutely right. And I think some people who kind of attack assembly theory say this Kolmogorov and ignore it. I'm like, no, very much inspired by Kolmogorov complexity and logical depth and all these different techniques. So Kolmogorov complexity is, of course, the shortest program you can make to produce something, and logical depth is about the runtime for the running program to generate the object. Both of these require computers and require some infrastructure, but more importantly, because triggers people saying, no, everything's computational. So that's fine. but it's more about the intrinsic ordering and the fact there is a causal structure. And what I've kind of been showing in the last few weeks is showing how, say, Shannon information or Shannon entropy and assembly are different, because Shannon entropy doesn't capture causal structure.
Well, when you say Taxol has a causal structure, are you referring to the process that built it?
Yeah, so the really interesting thing that goes with assembly theory is when you get this complex object and you basically deduce that it's complex, right? And you look at the minimum path to produce that object is a minimum, it's a bound. That allows you to say, oh, probabilistically, this is where there's some kind of, with kind of Judea's kind of type reasoning, probabilistically it couldn't just form. But what it does is it gives you a depth in time, the amount of time that had to elapse for that thing, for the universe or the system, let's put it, to learn how to make it. And so you're able, by cutting it up and having that ordering, you have that minimum bound that gives you a starting point. In reality, most complex objects will require more information than in the minimum bound. It allows you to compare it with the random background. And from that point of view, it's very parsimonious, and it allows you to be much more objective and be independent of the language. The only thing that constrains things in assembly theory, molecular assembly theory, is the bonding. And that is related to the laws of physics and quantum mechanics. And you go up a level from, say, assembly theory of molecules to, say, proteins, then you take it up another level, which would be folding. And then you go to cells and look at the surface of cells. And you go up to language and also, dare I say it, intelligence. We can get to later that you can look at the reducible parts of the thing that produces the object. As long as you prepare them correctly, you can do assembly theory.
Great. Can we try an example where we look at a piece of language, like a sentence or whatever, or even a human, or just something that's like more abstract and high level than a molecule, and calculate its assembly index?
You can, but what I've got to do, I mean, this could take quite a long time. The thing, when you think about it, let's think on a keyboard, and a monkey keyboard is a good one, right? So someone typing on a keyboard and an individual making a number of different parts. What you want to be able to understand is, when you have that sentence, where did the causation come from for that sentence? That causation has come from someone typing on a keyboard, intending to press a letter. Say the big brown dot, it jumped over the lazy cow, right? So now you can then take that sentence and then say, well, look, I don't know the person did it. In the same way I don't know how the molecule got made. But I can look at the assembly index of the sentence. And then what I need to be able to do is assert the copy number. Because there's two really interesting things in the data streams of assembly theory. Each molecule is a discrete object, with a beginning and an end. You can hold the molecule in your hand if you like. With text, you've got to decide what your delimiters are. And so it is possible and principle to do assembly theory on it and actually work out when text has structure, just from the repeat units, which goes a little bit further than just using compression, because you get these causal structures out. But this is something that's work in progress right now.
So in this example sentence, the big brown dog jumped over the lazy cow. So if I give you that sentence, do you have to know more information about where the sentence came from, or can I just give you the sentence with no other context?
My impression is you should be able to give me the sentence with no other context, but we do need to understand the context of the messaging, because I'm really interested in looking at this. We're looking at, say, radio frequencies and looking for information Carl Sagan style, right? If you want to find, has somebody encrypted information, or are you receiving noise? I think the answer to that comes in one sentence or one phrase, the copy number. If I give you random noise, it's random noise, and you draw it, and then I give you random noise again, and it's identical, you're like, well, that's weird. And I give it to you again, and the copy number goes up, and it's truly random, but actually is not random because it keeps repeating. You know that something has produced that random process.
I hear you. I guess I'm just trying to put an input-output framework around this. So like in the case of Kolmogorov complexity, your background assumption is maybe like a certain model of computation, like define what mathematical structure a Turing machine is or something like that. But once you have that, the input is a bit string and the output is its complexity, right? Like a single number. So like, yeah.
Yeah, sure, but the bit string is infinite with respect to the language basis, so that then it becomes, if you do the analysis properly, becomes really quite complicated. Like, what is the language in which you're going to do it? Because the bit string then increases in length, your bin size becomes bigger, and then it becomes rather unwieldy. So again, we're very confident in this. Because the reason why Kolmogorov doesn't capture ordering is it's language dependent. And even though it goes to a bit string, and that's fine right now, our technology uses bit strings, that's fine. If we want to compare things as bit strings, you can compare them using some approximations to Kolmogorov, because remember, Kolmogorov is not in the limit computable. The Kolmogorov is.
Yeah. No, I hear you. I mean, I'm just trying to clarify. So you have this concept called the assembly index, and it's going to output a number, right? Like you gave the example of outputting
it will
something
output
23.
Ordering of causation, and you can count the number of things that are in that ordering, and that gives you a number. And then, but that is with respect to a copy number. So you've got this kind of almost like this vectorial representation in object space, right? Something like this. But I don't know. We're still working on whatever representation.
So I'm still a little bit confused on what inputs does this function require, right? Because like we use the example of like, okay, a sentence can be the input, but it sounds like you might need additional context besides the sentence. So I'm just curious, what is the sum total of all the context you need in order to get this output?
Oh, you know,
ordering?
the beautiful thing about assembly theory of molecules, you measure it spectroscopically. You don't need to do anything. So look, so the theoretical framework is take a representation of the molecule, let's take it represented as a graph, chop it up into the parts, where you, in this case, we chose that hydrogen atoms are excluded, and look at the number of parts, right? You can do that. That's a mathematical process. You can write a computer program to do that. You can do it precisely. It can take a long time. Fine, do it. No difference. But then what you can do is you can actually measure the assembly index in physical reality using spectroscopy and other things. So this then suddenly you start to say, oh, I've got a theoretical framework which tells me about this thing. And I then can go and measure it in reality. And there is a correspondence. Not only that, I can find the assembly index is invariant with respect to the different technical measurements I use to measure it. So there's lots of different techniques you can use, different types of spectroscopy that don't depend on one another. And that's kind of interesting, and it tells us we're really homing in on something. It's kind of my favorite, inspired by one of my collaborators. My favorite book I'm reading at the moment is called Inventing Temperature. It's about the measurement of temperature, because people try to work out, what is hot and cold? Is it objective? Does it really exist? And this is kind of a similar problem. It is wild to me that scientists and computer scientists and philosophers are still not really making sure they understand what measurements are and what a theory is, what a model does, and what a computation is. They're all subtly different, but they should converge, right? And so the assembly theory was born as a abstract measurement idea in my head, actually. And now I realized I could measure it before I built the theory. And what happened after I was measuring, I can measure it, and I built a theory, if you like, or built the algorithm to assembly index. I was like, oh, I've got this thing I can calculate. I got this thing I measure, and they correlate. So that's kind of cool. And then we kept going and going, showing how it correlates across a wide spectrum of different measurements. And then allows you to conclude that the assembly index is an intrinsic property of the molecule, whereas the Kolmogorov complexity is not an intrinsic property of the thing, because you can represent it in different languages and get different Kolmogorov complexities. And that's why it's hard. It's really subtle, right? You're asking super good questions that are pushing even me, and I want to make sure, and even me in terms of thinking about this clearly, trying to make sure there's no BSing in the response is just kept very clear. So that's very good. So I like it.
Great. Okay, thanks for that. Yeah, I feel like I could spend more time on assembly theory because I'm still a little bit confused. But
what confuses you? I don't understand.
So I couldn't tell you the input output stuff even after all that.
What do you mean? I mean, the input is a molecule and the output is a number.
So I think I do get that on the level of molecules, but I'm confused when we talk about things that aren't molecules, right? Like a sentence. Is that the only input you need?
I mean, So we're working on that, right? I could BS you, but the input, let's look at a gene sequence. What are the input? The input is the gene. What is the output? The assembly index of the sequence, ATGC. So the reason why I'm reluctant to be nailed down to language is the variation of the causal structure that gives that is non-trivial. And although I have some frameworks for this, is an active area of research right now. What I can say with certainty is I can measure the assembly index of molecules. I can measure the assembly index of genes, of proteins, of cells. When you get up to higher abstractions, you've got to define the objects and the copy number really precisely. And we've done some with some cryptography, which is super cool. But I'm not ready to talk about it because I think I'll add more confusion than excitement to the conversation. So I take what you're saying. I don't know either what the best representation of the inputs and outputs are. I know the input has to be a sequence of some way, and I know the output has to be a count of the irreducibility of that, and there has to be a copy number with respect to that. So maybe you'll have some ideas what language and can come back to offline.
What about this example? So I give you a strand of DNA and it's just all A's. Okay, so it's like 1,000 A's in a row. So how would you calculate its assembly index?
If there's 1,000 A's in a row, then it basically, and they're all the same, are reducible, then the assembly index will be 1.
Because in some sense, you could have just copied and pasted 1,000 A's and that's one step?
I mean, well, the way I would do it is actually, it wouldn't be, if you gave me precisely 1,000 A's, then it wouldn't be 1. Because what you do is you start with A, you double it again, you keep doubling it, and the minimum doubling is to get to precisely 1,000. If you're able to give me a copy number of those 1,000 A's, like say 1,000 A's, then I could calculate the assembly index and say, hey, that's interesting. You've just given me a polymer which has no distribution, no statistical distribution. You've given me 1,000 identical copies with 1,000 A's.
So I have to also give you the copy number in addition to giving you the string of 1,000 A's. So I give you 1,000 A's and then I just give you like the number 3. Like, how does that work?
Well, what do you mean? You give me 3 lots.
Or can we do an example? So I give you 1,000 A's and you're like, okay, you also have to give me a copy number. So which copy number might I give you, for example?
The sample you give me, the DNA you give me, you're giving me a sample and I have to measure it. To measure it, I'm not just going to do single molecule DNA measurement, am I?
I don't know. I don't know what you're going to do.
I mean, it's hard, right? You're going to have to get statistics. So this is where the subtle interplay in assembly theory is there is no causation without a copy number. Otherwise, it's just random. This is the thing which fries people's brains. All assembly theory does is say, hey, if I can find an object that's precisely has an abundance, a precision, and monodispersity of lung, and I have identical copies, and the index is worth paying attention to. If I don't pay attention to it. So it's random nonsense. I can give you 10 A's, 1,000 A's, 776 A's. There is no causal structure that got there. And I think that's all it does, right? And I think that's a super important clarification. So thanks for persisting with that.
Okay. So I feel like I might be beating a dead horse, but like in this particular example, if I give you 1,000 A's, what is the output going to be of the assembly index?
Well, again, you need to give me, so if you give me 1,000 A's and and it's just one strand of 1,000 A's, how do I measure it?
And you mentioned maybe you're going to take like the log base 2 of 1,000 because it's how many doublings. So is that the answer?
You're in the limit, you can estimate that. But again, it's about the measurement. In this case, if you want me to calculate the assembly index exactly, I can do that. But I think that there's something more interesting that you've got to assess the copy number. Where did you pick 1,000 A's from?
Okay, so that's an important thing that I have to give you, right? I have to give you like some description of where I got the A's.
No, you just have to give me the sample. So there's 2 things here, and then we probably should move on. Okay, and you could give me an arbitrary object that just give me a representation of Gromov and say calculate a single index. So it's 1,000 A's or 1,000 B's, it doesn't matter, we can calculate it. There's the assembly index, right? And it's an irreducible representation to get there. We start with an A and just double. When you do, you get 1,000. It's easy. And in the limit, you can calculate that. No problem. But that doesn't mean anything unless you can actually measure that object. I can count the assembly index of anything, I could calculate the assembly index of the number of quarks in my glass. And it would be a lot. But it has no meaning if I can't precisely measure it with the resolution with which I've done the counting of the assembly index. And that's really important. That's what grounds it in experimental reality.
Okay. All right. Got it. Is that a good place to leave it?
Yeah, I think so. It's good. Good. It's
Cool.
good. I like it, like the Cushing.
Great. All right, Professor Cronin, are you ready for the next segment?
Do it.
Hit it.
P-Doom, what's your P-Doom? What's your P-Doom? What's your P-Doom?
So, Professor Cronin, what is your P-Doom?
For what? The end of the universe? The end of the Earth?
Let's say essentially human extinction, or all the value that we might like to have in the future wiped out at least 99% or 99.9% to like basically a huge disaster for humanity. And let's say on the time scale of just by 2100. So the probability of that kind of catastrophe.
By the end of this, I mean, there's zero.
So there's just zero chance that humanity is going to get wiped out by 2100.
Well, I mean, so let's think about this logically. The only way that humanity would be entirely wiped out is if a catastrophic object hit the Earth or the sun suddenly exploded. I could imagine scenarios where we had nuclear wars and other things. It would be very difficult to wipe out all humanity by 2100. Not inconceivable, but I wouldn't understand how to put a statistic on that. You know, one of my favorite apps I've got on my phone is called Am I Going Down? Which is basically, you look at your plane and you go to fly and you basically you pick the worst airport, the worst aeroplane and the worst carrier, and it will say, right, you know, statistically, if you fly this flight, you know, every day for 600 years, you'll go down once. Whereas if you then basically, you know, pick the best airline, the best airport, the best plane, you never go. You have to fly for 26,000 years. The problem I have with these P-Do things is it's forcing me to have some indication of the priors. But let me, you know, and I mean, Scott Aaronson was doing this, like, you know, there's a 1% chance. I'm like, there's not a 1% chance, right? Human beings have undergone catastrophic extinction level events in the past, right? So did Neanderthals. So you gave me very precisely a 2100. So we are in 2024, right? So we're talking about 76 years away.
Right.
I can do the mathematics properly, okay?
Yep.
So the chance of human beings going extinct, every single human on planet Earth, by 2100, I think is very low, if not zero.
Okay. So I think I know the answer, but I want to ask you anyway. Would you sign the statement on AI risk that says mitigating the risk of extinction from AI should be a global priority alongside other societal scale risks such as pandemics and nuclear war?
So look, if I was going to be nonchalant, I would say no, but let me be thoughtful. I don't know. Like nuclear war is worrisome. I don't want nuclear war. I don't want a catastrophic runaway climate change or anything that's going to happen. I think AI as currently posed doesn't feel like that type of problem. However, I do not think it is reasonable for me to rule out the invention of a technology that wouldn't merit me signing a document to say, hey, stop doing that. Right?
Great.
And I think that that's me giving you an unexpected branch. Just look, I don't think AI that we have right now is scary at all. But that doesn't mean that we might not invent something that we do need to think about as containment. I mean, let me make something up. I don't know, and I don't think we'll ever be able to do this, but a virus who's just good enough to replicate and basically only kills humans after a certain amount, with certain incubation periods, so we can go around and cover everybody, a bit like Omicron. Omicron, I think, infected everyone on the planet, and then basically hit the ribosome and everyone drops dead. There is a non-zero chance somebody could engineer something like that. It's very small.
Exactly. So it sounds like you subscribe to this background assumption of like, look, it is still kind of a fragile world, right? Like eventually the sun's going to burn out, or if we give it like 100 million years, eventually there will be like a major asteroid impact, right?
Yeah, I mean, if you give me, so I oscillate on this. I'm like, well, someday a super optimist to say, there is no challenge we cannot overcome. But I think it's arrogant because I think, that might allow us to not plan, right? Why not have a why not have an asteroid defense system? That's a great idea if you have the resource. Why not have an ability to stop nuclear weapons from going off? And why not, if there is some technological intelligence that we can generate, that let's say it's possible to generate, that we wouldn't want to think about how we would release that and how we would use that. In the same way, you don't want to release a load of, so I'm a chemist, you don't want to release phosgene, which is really nasty gas. You don't want to do anything like that. So I do subscribe to local fragility, but not necessarily global fragility. I think some things will survive, but I'd rather that no humans died, that basically we're all fine. So from that point of view, I'm with you.
Great. And then bringing it back to AI, just for the audience's benefit, that statement on AI risk that I read, it was signed in 2023 by some heavy hitters, right? Like Sam Altman, Dario Amodei from Anthropic, Nobel Prize winner Geoffrey Hinton, Turing Award winner Yoshua Bengio. So a lot of serious people across.
Described by, sorry to interrupt you, heavy hitters, people who are not trained in philosophy, who don't really understand the scientific methods. Or, I mean, if they...
Well, I will say the late Daniel Dennett signed it, so I think you got one exception there.
That's not fair. I love Dan, he's great, and I would love to have argued with him about it, but I think... Oh, that's a really interesting one. Why the hell did Dan sign it?
A mystery. But yeah, just to frame the discussion here. So a lot of heavy hitters signed the letter in 2023. So basically the position you're going to take when we talk about AI is like, well, these guys mostly aren't trained in philosophy, and so they're just wrong about seeing AI as a potential extinction risk.
Well, let me make something up for you. I'm afraid of anti-gravity, right?
Sure.
I think it's physically possible that somehow that gravity could be turned off. And if gravity gets turned off, we're all going to float away. This is a risk, right? I can imagine the risk.
Sure.
Yeah. The problem is it's a nonsensical risk with respect to what we know about the laws of physics. That doesn't mean, but it is a bit arrogant for me to say there is no chance of AG, but I think you would probably agree that AG is not something that we should worry about. Because then there's another risk. What about spontaneous water boiling? And so,
no, absolutely, right. I mean, I agree with your framework, right? That like all of these theories might make logical sense, and at the end of the day, we just have to argue, like, okay, what does the evidence indicate is like the correct theory, right? Okay.
And Altman's and of the world, and Geoffrey Hinton, like he was just making stuff up. I mean, I have no idea where that came from. Like the fact he doesn't understand how a neural network works is wild to me. Absolutely wild that the Sepulveda didn't actually create it, but let's say he did. That he basically now thinks that these systems are intelligent is beyond parody.
All right. Well, I'd love to unpack that claim because I think that sounds like you're going out on a limb, right? Because you said Geoffrey Hinton doesn't understand how a neural network works. So maybe to unpack that,
what I'm just going to qualify it.
Okay.
So Geoffrey Hinton, he either understands how a neural network works, and if he does, the statements he's making about intelligence are actually disingenuous. And I'd be happy to talk to him about it. And I'll explain why. And he's not here to defend himself because he goes on and says there is this genuine risk that the systems are intelligent right now. And that is not true. That's easy to falsify. And it comes out that these people think they understand what intelligence is. And it goes back to this argument of like, can we define intelligence? Now, I might be going some way the other way to say, who am I to say that these systems are not intelligent? And what I can do is and again, it's about the limits of probability. So what you're saying is like, I understand neural networks, that Nobel Prize, well done. I think it's awesome that you got it, by the way. But they're intelligent and they're going to kill us. Like, those two things are just really weird. It's like Jekyll and Hyde.
So some context about Geoffrey Hinton's views from the public statements I've listened to. One thing he observed is that a few years ago, he said that he got shocked when he was playing with the AI, and he was shocked at its ability to learn and generalize. And he even got the sense, according to his own words, that it's now better at learning concepts than the human brain. And he was just shocked how deep learning got to that point faster than he expected. And then furthermore, the kind of thing that he's worried about is he thinks within a few years, to use his words, AI might become a master manipulator because it would just learn, the art of manipulating humans, the Machiavellian arts, basically, and just essentially go out of control. Like he's even floated a number like roughly 50-50 chance that he's just worried about a scenario where we just keep building too fast and it goes out of control. So what do you think about that scenario? And then we can talk about, I guess, what is intelligence?
I actually don't disagree with Jeffrey's worry about something going out of control, but it's not the AI, right? The thing is, what is going out of control? It is the human beings using the AI to manipulate people, right? These technologies are extremely powerful, and there's no question, but the AI doesn't have any intentions or agency. And I can explain that very simply in a way that will cause very good discussion. That the thing is, the AIs don't suddenly develop an intent. And I think that probably what I've observed with these, and again, I don't mean to be rude about these guys, but I see like I'm seeing the emergence of a new religion, right? And there is basically people saying, AI is good, AI is going to save you, AI is bad, AI is going to kill you. But no one's actually saying, what is AI as we use right now? And you're absolutely right. You and I, we could get some bots together and we could put disinformation on it, they do it correctly, about an election, or we could manipulate some images to make people outraged about something. That clearly is a threat, but that is not the AI. There's a naughty human being in the basement doing the thing. And that has been going on time immemorial. So why suddenly it said there? Now, I would get behind, because this is where I agree with Jeffrey and Sam and all the guys to say, actually, I don't think Sam will agree with this. The thing I want, authenticated users and authenticated data. If I have these in the public domain, I will be willing to sign a document to say, hey guys, the biggest threat we have is that we don't have authentic users or authentic data. That we're just stealing all this data, doing all this stuff with it, and we're using it to incite violence or whatever. That's a worry, but that's not the same thing as an AI turning on humans and doing bad things.
Okay. Let's drill down into where you say you don't see software having agency or intent, and there has to be a prime mover. And I think you would argue that the prime mover has to be like the human who ran the software or who created the software. Is that your claim?
I mean, for me, the reason why I feel so interested in this is like, for me, I'm trying to understand the origin of life, right? No origin of life, no biology. No biologist, no biology, right? No philosopher, no philosophy. So basically, there's this causal chain that connects us all the way back. If there's no origins of life, there would be no technology right now. And that's really interesting. And so it's not just about the programmer, not just about the user or the prompter. It's the person who developed the model, the mechanical Turk that interrogated that, the person who designed the semiconductor, the person who did the lithography. And there's this causal chain of objects all the way back that basically put it in. Now, I don't know where intent comes from macroscopically right now. It's one of my big questions, right? Origin of life, origin of intelligence, origin of consciousness. And I don't know what that is, but all I'm pretty sure is that when people see intention in these algorithms because they're running, they are actually seeing crowdsourced intentions that have happened in the past.
Let's do an example scenario, and then we can see how your model of agency and intent can apply to the scenario. So scenario is pretty simple. Imagine somebody builds a rescue bot in the next few years, and it's kind of like a Tesla Optimus, it's like a humanoid robot. And what it's built to do is like pick up patients from like the scene of a fire, like maybe they're helping a firefighter and they just want to rescue somebody and they want to carry them to safety. And maybe safety is even like a block away from the harm. Okay, now safety bot, maybe it doesn't have intent, maybe it doesn't have consciousness, it doesn't have a soul, but it gets pretty good at accomplishing the mission, even if you throw up obstacles. So for example, if there's like a lot of rubble, it's really good at like climbing around the rubble, and maybe it can even like put the person down and go clear some rubble and then pick the person up again. And then if somebody tries to stand in its way, maybe it can even like shove the person out of the way, right? So it starts getting really good at just getting to the rescue mission. So do you think there's any intent in that scenario?
No.
Okay.
Take a
Yeah.
clock. I design the clock and I wind it up, and every day it keeps ticking and gives me the time. And it keeps giving me the time.
So the difference between just giving you the time and the scenario I described is that you can notice you can vary the initial conditions through an exponentially large space of initial conditions. Like I can set up the battlefield for this bot in so many different ways. And no matter how I set up that initial battlefield, it's always going to somehow route a path to the same destination.
I can put the clock in lots of different initial conditions and it will still do the same thing. I mean, the clock, if I could put lots of clocks together, right? Let's say that they've somehow got some weights on them and they work with one another. They will also have kind of interesting deviations. So no, I mean, it is really important that it's clear that what we're talking about here is a program that's been written or developed or evolved, depending on how you want to do it, right? By a person with an intention to do a thing. I mean, I love mechanical robotics. You know, I don't know if you've seen these robot arms where you can have a robot arm and you pick up an egg, right? And I don't know, I'll pick up my earbuds here, right? But let's just imagine this is an egg. If I don't get the force feedback, I can crack the egg. But one of my colleagues at Harvard years ago made an inflatable robot where they basically the arms go down and they inflate around the egg. And you just had to use wrong pressure actuation, and then the elasticity would pick up the egg without any force feedback. It just didn't crack the egg. Now, that's a beautiful example of a kind of what I would call a morphological computation, where the material scientist thought about the computation that was going to be done there. There was undoubtedly a computation done, and they didn't need any feedback or any advanced electronics, but it was able to accomplish the objective of picking up the egg without breaking it. And so and again, it was designed and created. And so I think that this is a really important point that we can spend a lot of time digging into. Sure. It's like, you know, there is a combinatorial space, and we can talk about when that combinatorial space becomes really interesting, because that is a limit of what we don't understand, right? Where it's like, what is intelligence?
Let's go back to the example, because I think we can still squeeze some juice out of this example of comparing my rescue bot scenario with your clock scenario. So the thing about a clock is that you don't get the sense that a clock is hell-bent on telling you the time. For example, if it's an analog clock and I reach in and I perturb the dial, so I set it 5 minutes forward in time or whatever, it's not going to then reset its own dial, right? It's just going to keep telling the wrong time. Whereas RescueBot, if I push it over in the scenario, RescueBot is programmed to realize, I'm going to do better if I stand up. That's going to help my rescue, right? So it's hell-bent on completing the rescue in a way that a clock isn't hell-bent on giving the right time.
Let me give you a converse. Take a buoy, or I don't know what the American, an buoy in the ocean that has a weight on it to stay upright. They have a pendulum. You push it over, it comes back up. It's just physics. You encode
this is right. So this is an interesting example. So you might think that I'm saying, well, doesn't the buoy have intent to rise to the surface? And my answer would be the space of initial configurations. It's like, okay, well, you can give it like latitude and longitude where you put it on the ocean, and you can give it an initial depth. But that's a pretty tiny state space compared to what I'm describing with RescueBot.
But you've just answered your question. You're talking about, and actually the state spaces aren't that different. So when we start to look at where human creativity comes from, decision making, it comes from the fact that the state spaces that you search or you occupy, they're just so big. And so I have sympathy for, if your argument is the robot's got a big space of things it has to solve for, that's cool, isn't it? I'd be like, sure, but the program is controlling that. And also, you have to build in contingency into that program because it has to anticipate the unanticipatable. But what it does is a local search problem where it says, if this happens, then that happens, and this happens. Within that state space, it's very deterministic. When you nest them all together and you allow some variability, it looks non-deterministic, which is cool. It gives us emotional feedback. You could even put eyes on it and a little smile. And they go, oh, look at that lovely little robot. Isn't it doing a good job by saving that person? You know, Sure.
Do you think RescueBot can ever get to the point where it can solve the rescue problem as good as a human teleoperating it could do?
Yes. But again, the human encoded it to do that. RescueBot didn't emerge out of the sand. It came from a origin of life, Luca technology, lithography. So sure, we're going to RescueBot is going to get better and better and better, and it should be able to save all humans.
So, I mean, I agree with you to the extent of like when you look at something like a rescue bot, I do think we can make the inference of like, something programmed this to be a rescue bot, right? So there was a preceding important piece of causality. And this is actually similar to the watchmaker argument. Here, I even wrote a note about this. William Paley's watchmaker analogy, you know what I'm talking about? Yeah, so right, so you find a watchmaker, or you find a watch on an island, and you look at it, and you're like, okay, this didn't just like wash up naturally, right, from sand mixing, right? Like there was clearly I feel like I'm in your wheelhouse, right? Like there was clearly a long causal process that led to this watch. So I agree that you can do the same thing. Like, yeah, RescueBot didn't just spontaneously arise. So I agree with you there. But at some point, if I'm just like surviving in an environment with a bunch of rescue bots, doesn't it become kind of irrelevant to how we're going to interact? The fact that, okay, they were initially created by human programmers, but now they are just really effective rescuers, and the world, and everybody's going to get rescued, right? Like, isn't that the correct mental model of the world?
I didn't disagree with that. Oh,
okay, great. So I guess maybe we're just, at this point, maybe it just comes down to a semantic disagreement over the word intent. Because for me, when I look at a human and I say that human has intent, I'm not feeling a difference in kind between RescueBot's intent to perform a rescue and my own intent to go get myself some chocolate when I'm hungry, right? I feel like they both fit a similar type of intent.
I think you're touching on something super important that I think the thing that human beings will never cease to amaze, I think was, and I would love to talk to you in about a year once we get bored of AI as currently conformed, right? Is that of course, there's a certain amount of behavior that you can just model, right? Hunger, it makes people angry when they're hungry is good fun. But if you give someone enough, if you observe someone from long enough, they do this thing you were not expecting, was not in the data set. Do an out of distribution thing, right? And depending on how far out of distribution, we would call that creativity. And that creativity is really weird. And there is no question that the current AIs are showing that humans aren't creative as much as we think they are, right? On some levels. On other levels, they are incredibly creative and they do things very different. And in a very primitive way, it has something to do about the size of the combinatorial spaces you have available, right? To be surprised by. So sure, I can probably guess what you're going to do. I do weird things, like I take different routes to work. I might go clockwise one day, anti-clockwise. Why do I make the decision to do that? Where did that come from? It still fascinates me then. It's just a cell, like a couple of cells that you could just birth from a parent should do the same things, but they don't. And you're like, why? Where does intent, that variability, that kind of come from? Well, it comes from obviously from genetic differences and microscopic environmental difference. But is that all there is? Is there no hysteresis in the cell? So
yeah, let me zoom out of it because I want to make sure that I understand and the listeners understand kind of the high level position where you stand on artificial intelligence. So maybe let me ask the question like this: like, what do you see as the barrier or the separator between software intelligence and human intelligence? And do you think that barrier is going to last forever, or when do you think that barrier is coming down?
I do not know how to define human intelligence right now. I mean, I have an idea. I'm writing a paper on it with my colleague, and I don't want to give too much away, but we should definitely talk about it because it has something to do with assembly theory. But right now, I would like to, the fact that we found it really hard to define life, right? This is what happened in the origin of life. I could see the same thing happening in intelligence. And I think what happens is because everyone had an emotional response to what they created. So I'm going to say, and obviously you're not, these guys, you'd have to really get the mellow and say, look, you had an emotional response. Why did you have emotional response? And we do have feelings invoked. But coming back to what intelligence is, I find it hard to define what human intelligence is. And also, I do not think that the term artificial intelligence is actually a gross misrepresentation. I would just call it, I don't know, autonomous informatics. Now, why autonomous and why informatics? Well, exactly go back to your rescue bot thing. I've programmed it. I've made it autonomous. It can get charged. It can wait and do stuff. That's good. And it's processing information in the environment. It doesn't need to come back to me. It just does its thing. So for me, the word autonomous informatics removes all the anthropomorphisms, removes the emotion, removes the things that that humans are projecting onto things, and it's just the thing. Now,
Yeah,
what
great.
did you? Go on.
I think I can ask you. I think I can ask you a question where the answer doesn't even depend on semantics. Choice of definition. It's just a question about predicting reality. For instance, a question like, "Hey, 100 years from now, what is a human job or task that you still think humans will do better than AI?"
A human what task are you? A
So
job
100
or task? Oh, right,
Yeah,
yeah.
exactly.
Oh, poetry, music, all these things. Creating new technologies, finding the next generation. There is another. So the thing is, and this is my number one comment I have to make, which I really, I've thought very carefully before coming on about how to put this across, where hopefully I would win as many friends and influence people in a good way, rather than just be obnoxious and just say, I do like using AI tools for certain things. What is AI tool a great thing for? It's great for taking a historical data set and telling me all about it and just interrogating it. So AI is backward looking intrinsically, right? And so I think that AI tools in the future are going to be used. So will the poets of the future be using AI tools? Sure. Why wouldn't you? You'll be using it to augment the processes that we're going through. So I think that and lots of tasks will look automatable in the short term, and AI just fails to do them because the edge cases are just there forever, right? And
Yeah, can we unpack the music example? Because I find it pretty surprising that you're predicting that 100 years from now humans are going to be better than AI at music. But it sounds like maybe you're making a weaker claim than that. Maybe you're saying maybe in 10% of times when you need somebody to write you a song, there's going to be 10% of times that the AI is not going to get. But it sounds like you're kind of admitting that maybe 90% of the time the AI will be fine.
So let me be qualified. I mean, on my Group Away Day a few months ago, they made an AI generated song, and it was brilliant. But they gave it prompts. They gave it prompts from the lab and things they were doing. And so what AI will do, like any tool, it will lower the barrier for creative people to do things. And I think then, you and we could go write a song and I used to write a lot of electronic music. I like doing it. It's cool. But will I use AI tools to do it? Hell yeah. I can explore spaces. I use Cursor right now because Cursor just allows me to not dig into a rabbit hole of dependencies. Just says, Lee, you're not paying attention. Your ADHD is really bad today. Here's what you need. Run it. And so these are tools. It's a bit like people going, how did you use a test tube as a chemist? You should hold the hot stuff in your hand. Like, I don't get burned.
Right.
So going back to
I know you call it a tool. Yeah, go ahead.
Yeah, what I mean is, so going back to the jobs, I think that AI will basically allow people to have much more access to doing these creative things at a level that you say is 90% good. And it's not saying that we won't use them. Of course we'll use them. I mean, we get textiles made and stuff. I'm not saying they're not there. I'm just saying the human is always going to be in control.
Okay, human's going to be in control, but the question I was asking, to be precise, is like, let's say it's 100 years from now, and I just want a little jingle, like the segment of this podcast where it asks, what's your PDoom? And I made a jingle for it. I used AI to help me. Let's say I use a human composer, and I interact with the human composer over Slack or Discord, right? Because it's a virtual, they're working remotely. And I just say, hey, here's my requirements. And maybe they ask me a question, and I answer the question, and they send over an MP3, and that's the jingle. Now, you're telling me that 100 years from now, I can't replace the human with an AI and get an equally good work product?
Yeah, I think so. And here's the thing right now. I see a tendency right now. If you look online, all the websites that say, all the generating art is to say, if you want to make a good podcast 100 years from now, sure, you could get cheap stock stuff, but you want that, and you want that little edge, and that edge may look smaller and more intangible. I'm guessing so. I'm willing for you to change my mind, but I just don't see any evidence.
So it just feels like you're not extrapolating the progress of AI from like last year to today. Extrapolate that forward 100 years. It sounds like you're kind of just acting like it's the same as it is now.
Yeah, no, I can prove on the back of an envelope why it isn't going to go up. It's a data training issue, right? Like we're just at this asymptote of what we can do with the technology we have right now. Now, is that because there's a technological limitation, or we only can get so far at faking some intelligence or creativity? I don't know, right? What I will say is I'm very happy to, I'm not conceding it. I would use the tools, but I think human beings will be doing what they're doing today, largely. We might have more automated. We might not be doing some things. Like what job was happening 50 years ago you wouldn't want to do today, right? There's probably lots, right? Lots of labor. Sure. So I think that there is that. So I think that there is, on the creative side, human beings are going to be always better than AI.
Fair enough. Okay, that's another topic I'd like to dive into here. Let's see. So you actually tweeted a couple years ago. So I love that you're coming on the podcast so I can bring up your old tweets.
What did I say now?
So you wrote, algorithms cannot be creative by definition. The human brain can be creative. Therefore, the human brain is not just algorithmic. So let's unpack that. Why can't algorithms be creative?
Yeah, this is the most important point, I think. I still stand by that. That's quite a good statement, actually. So what is an algorithm? Tell me your definition of an algorithm so we make sure we're grounded.
Sure. So high level, it's following a step-by-step procedure. And then we have to talk about, okay, what is a procedure? What are the building blocks of a procedure?
Yeah, well, not wanting to like got you. It's just like, I think it's just...
Yeah. Well, the nice thing is that today, because we have computers, it's pretty easy to be like, hey, we're not even talking abstractly. It's like, I can just open up a Python editor and whatever I can type that passes a syntax check, that's an algorithm.
Yeah, I think that's fine. And so if you're talking about what creativity is, now let's define creativity. Now for me,
sure,
creativity or novelty, we can do the two things. So if I find something or something, let me get this right. I need to be as precise as possible. Let's say I discover an object that is basically, I have no precedent in my data set, right? For me, I mean, like, that is the most novel object that's come into my data set. Maybe I can do a distance measure. But let's say I start with an empty set. Everything I put in by definition is novel to start with. But I put in a pineapple, I put in a banana, I put in an apple. But then at some point, I'm like, oh, I've exhausted the set of fruit, so I can, right? They all look the same. I picked up another grape. It's just a slightly different grape. It's moldy or whatever. So basically, the elements I put in my set, right? When you're generating data algorithmically or you're processing data algorithmically, creativity is saying there needs to be some creative input from somewhere. Now, I think this is where a lot of machine learners get things in a bit of a pickle, because it's like saying that it's a bit like you're getting something from nothing. If I take a data set and then I use that to create another piece of data, there's a causal relationship between that using the algorithm, like the inputs from somewhere. And so if that outcome has always been interpolatable from my data set, it's not really creative. It's already there. Now, maybe I interrogated the data set in a creative way and I get something out that surprises everyone. That's possible, right? There's some of that. But in principle, what I think I'm saying is that the act of something creative has to happen to you interacting with that data set. The systems are creative on their own. And because you can't generate something from nothing, it's dependent upon the data there and the system that you've built.
Okay, well, so now I get curious about I wonder how did the creativity even enter the human brain? So let me ask it to you this way. Can a simulated brain on a silicon substrate be creative?
It doesn't appear so. And I'll tell you why. So the problem is a brain has about, I don't know, is it 100 billion, 120 billion neurons, let's say a trillion neurons, right? And the way the neurons work is that each neuron is about 10,000 connections. And those connections are moving in real time. So this statement is kind of important. There are more possible connections in your brain than there are atoms in the universe. More possible.
For sure.
And so what seems to be happening is as you interact with the environment, you're getting in sensory information. Your brain is constantly shifting and shaping and doing stuff, right? Some boring, some novel. But the fact your brain has access to that configuration space produced by evolution, growing morphologically and all this stuff, means your brain is literally able to do things that you cannot correctly model yet. I have a project in my lab called ChemMachinet, where I'm trying to make a chemical brain. And I reckon the best way to get to creative stuff is to actually make a chemical brain. There's nothing magic in the brain right now, other than we do not understand how the brain is able to traverse these combinatorial spaces. But silicon is hard, and you can't reconfigure your silicon. So the resources required to basically simulate a brain are just exponentially large. So it's just a large problem. It's an energy problem as well. So I guess, I'm a really deep materialist. I don't think brains are very, very, well, they are the most complicated thing in the universe we know, which is kind of amazing, right? And I think that, even NVIDIA, who are making some damn good hardware, are making hardware anywhere near the complexity or the configurational accessibility of the brain. And that's my only argument, really.
I mean, I think we're getting to the point where a trained modern AI, with trillions of weights, potentially could be thought of as a more complicated object than a human brain.
So let's unpack that a bit. I think that a trained AI with trillions of weights, lots of parameters, is certainly incredibly powerful. And remember, object is the compressed outcome of billions of people's creative input put down on the internet and recorded, and then interrogated. And so I'm probably as excited as you are about using these tools to get to that stuff, because there's so much in there. But I don't think accessing that in novel ways itself is any more creative, because the poor humans that are probably now deceased that have put all that information in there were the people that did the creation.
Yep. And that's, that could be right. I mean, I was just making the point about how if you're just measuring by complexity and you're saying, look how complex the human brain is, I think that argument is losing steam.
No, I think the human brain can do something quantifiably different to these models, right? By many orders of magnitude. And it looks like, I'll give you a tidbit. Let me make a prediction. Within 2 years from now, I'll be able to produce the technology that will be able to tell the difference between human creativity and AI creativity.
Wow. That would be great, because we could really use that for a CAPTCHA.
I mean, yeah. And I think it's super important. It's not so dissimilar to how assembly theory tells the difference between a randomly produced molecule and a molecule that's gone through lots of steps, and the copy number. The way that AI interrogates the space by having enough entropy or temperature gives you because AIs are probabilistic machines, right? Right now, the Gen AI machines we use.
Okay.
And so that's as far as I want to go for the moment. I think you've asked very good questions. I don't disagree with basically anything you've suggested. You haven't tried to twist my words, which is great. And I do agree with you. And maybe the only point of disagreement, and it's not even that significant, is I think that these models are much less sophisticated than a human brain. But they do great things. But there is a lot of captured information in there that we aren't even beginning to touch. And that's why Geoffrey Hinton and everyone else got so excited.
And I want to clarify your position. So basically, I mean, so you say you're a materialist. So you definitely you don't think that there's some level where God is like whispering creativity into the human brain. You do think it's all based on physics, right?
Not the physics we have right now is not quite right. So the only thing that I would say is different, just to be clear, is I think that time is real. So this is where basically I can do it aside. Like, maybe this is going to sound pretty insane. Einstein invented relativity. He invented it, he introduced it. If it wasn't for Einstein inventing relativity, when we started throwing satellites into space, we would see the stats frame dragging and they were losing time. They'd be like, why is on that? We would add corrections to get there. But there is this abstraction, this underlying structure that we understand to be relativity. Right now, we are building systems that look creative and we don't understand what's going on. And there is a missing thing, and I'm going to make a suggestion what it is. And it sounds very hubristic, and the people that don't like what I'm saying are going to jump on us. I'm being really arrogant. I don't mean to be. I'm just saying the universe is like this in time. And so the future is always bigger than the past. So the future is always non-computable with respect to the past because it's so big. And that's where creativity finds the edge. The transition from the past through the present to the future, because the future is open-ended, it's so exciting to live in the present and the future going on. And that's why I think that we are kind of stuck, because we've mined the past is really good and it looks really great. But I'm going to argue that we're never, ever going to be able to, because time is a physical thing. And this is where a lot of these problems come from. So the only add-on to materialism is I think that physics right now has a misinterpretation of time. And the only thing I would change from I'm a materialist that thinks time is fundamental, not a emergent property. So sorry, go on.
Yep. Just to repeat back to you, your claim here, you're saying that, and I think you said this explicitly before, that no matter what algorithm we write, even if it's a huge algorithm with a ton of memory doing a ton of operations, the fact that it is an algorithm means it can never do the kind of creative outputs that you could potentially get from a human brain, correct?
And I mean, and the discontinuity here is to say, the human brain is not magic, it's physical, exists in time. And we should be able to reduce everything to some kind of algorithmic procedure. Therefore,
right. So by the way, also, it sounds like you're disagreeing with the Church-Turing thesis. Is that right?
And no. So yes and no. In the limit of the universe, yes. In little pockets where I capture things where I have a resource available, no, it works just fine. And so this is the thing, where the only reason that creativity is not computable is because we don't have sufficient resources in the present to predict the future. That's all. That's it.
Okay. All right. Fair enough. So I get that that's your position. And then going back to what you said, that you're hoping to produce a program that can distinguish human versus AI creativity. Let's unpack that a little bit, because if I go to a website and they're worried, they want to make sure I'm a human, right? So they give me the CAPTCHA test. And today I think it works by detecting like, what do your mouse movements look like? And what information do we have about your IP address, right? So they're combining all these signals, but those are becoming more and more fakeable by AI. So you're hoping to essentially have a better CAPTCHA where maybe a text box pops up and it says, give me a creative answer to this question, and a human types something in, and then your program can be like, yes, this was a human answer. Is that basically what we're talking about?
It possibly. I think what we're going to do is a little bit more sophisticated than that. But yeah, I would say, I mean, we're going to get better. I mean, the thing is, computers are kind of a low-dimensional output, right, for humans. Humans do lots of things. Non-verbal communication, singing, sighing, rolling your eyes, microaggressions, macroaggressions, all this stuff, but so I think that we might need to do a bit more than that. But yeah, I mean, I'm really fascinated by this problem. I'm really excited that we have these tools. I don't think it's a problem. I think the only thing I have a problem with is the one concept that we should perhaps discuss of super intelligent. That is the only thing I have a real problem with, where people do, and there's just because people are just making shit up.
Okay, interesting. So I guess I kind of got stuck on your claim that you don't even think any algorithm, even a really smart algorithm that we take 100 years to invent, you think even that algorithm, by virtue of being an algorithm, is not going to be as creative as current humans, because something that the current human brain is doing can't even be described as an algorithm. So once you said that, I guess I didn't even think to ask you about superintelligence, because you kind of already said, hey, we don't even have regular intelligence.
Let's go back a step. I think algorithm, so any algorithm that is computable kind of now, right, with the resource available, is never going to be as creative as a human brain. Because the human brain actually is the ultimate algorithm novelty miner, that it's using the resource available, everything available. The problem you have with your current algorithm is you don't have enough resource. And the only difference between the human brain and your current algorithm is there's just a resource accessibility. You've got all my neurons moving around doing all this morphological neuromorphic computing, whereas my poor algorithm confined to my silicon is constrained somewhat. So I think it's probably a difference of computability and resource availability. And that I think I would love to dig into and think about. There's so many research projects here. So I wanted to qualify that because I think it's a really important, I could be wrong, I need to think about it more. But, what's the difference between my brain that could be if I could froze me now and look at my brain and took it apart and you could express it as now.
And by the way, I think you do acknowledge that what you're saying about brains, I would say this is a non-mainstream or even a fringe position, right? Because you agree that the mainstream position about how humans are intelligent is because they're running a good algorithm, no?
I mean, I think the whole problem with this is is that we're trying to put our technological concepts as an ontology for understanding nature. And I think this is the one thing that I would like to mention that I'm only learning because I'm not a very good philosopher. And Dan Dennett would definitely agree with this. And maybe Dan Dennett was having a bad day. We've got to tell the difference between the ontology and the kind of the way that we use knowledge. That the universe is not a computer, but the universe allows us to build things, to do computation. Now, some people say no. Actually, the universe is a computer. And then you have this kind of argument back and forth about what we mean by computation. And so an algorithm for me needs to be containerized in some technology and needs to be executed and run. And I think, and it isn't, the brain is quite a large size. And I would argue to make a brain, make a technology is kind of as good as my brain, or maybe not. Maybe let's say your brain. Your brain is probably younger, better than mine. It's going to require a lot of resource, probably more resource than humanity has access to right now.
Okay. And, as I'm trying to step into your shoes and see the world through your eyes about how, brains are doing something that no algorithm can do. If I just think about an average person in the last 24 hours, what was an example of a non-algorithmic thing that their brain did in a typical person's average 24 hours? And the reason I'm asking about a typical person's average 24 hours is because you'd think if evolution by natural selection, would select this wonderful trait, this non-algorithmic intelligence, you'd think it would show up in a typical day.
It's our imaginations, our ability to have the counterfactuals and all that stuff. Of course, the average human being is doing this all the time, but we are being compressed into low dimensions in our digital media, so we're becoming kind of obsessed with what we're seeing. But no, with counterfactuals, imagining new things, coming up with new stuff.
Yeah, but in terms of outputs, right? So for example, let's say that my job is to flip a burger, and I'm like, hey, when I flip that burger, I just imagined like I was flipping it over the clouds. But that didn't really help me do the job better than an AI, right? So I guess my question is when does the average human on an average day use a skill that AIs don't have?
I think that happens all the time, and I think counterfactuals happen to humans all the time in selection. You can see that counterfactuals have causal power. And I mean, I will think about this and come back, but I think let's not insult the average human. The average human is thinking about maybe new partners, a birthday party, worrying about trying to get money for their education, solving problems about it whilst they're flipping the burger. There are mechanical things that AI can do, sure. But the average human is doing so many things in their mind with their imagination, maybe thinking about some art idea they've come up with, or maybe thinking about how to solve a problem because they've got this complex social issue out when they've got friends that don't get on with one another and trying to find a way that they can find an angle for them to be at the party together. There's so many things the average human is doing cognitively, psychologically, and creatively. It's not possible to compress them down into burger flipping. Sure, if everybody, I think that's kind of, the average human, even when they're flipping a burger, is doing so much more.
Great. Okay, nice. So we're coming up on the end of our time here. If there's any other topics you want to cover, I'm happy to go a few more minutes. Or do you think we hit on everything you were hoping for?
Well, let me just tell you about superintelligence, why it's a fiction. superintelligence is a fiction, because what has happened is that someone has said there could be this thing that just has access to some physics, is able to solve problems in a way that you can't conceive. Now, what is that saying? That's saying that this entity has access to new reasoning, physics, mathematics that you can't even have slowly. Because if I take my favorite pocket calculator, I love calculators, right? I'm always buying calculators.
Yeah.
This is my
TI?
favorite.
Oh, an HP, right?
I've got a few others. I love at school there's my Casio.
Oh, nice.
Look at another one. Look, I didn't think I'd be showing you my.
I was a big fan of the TI-89 in high school because it was right before anybody ever had a smartphone, and I love smartphones, so that was like my smartphone proxy.
That's cool. I mean, I love having these calculators. So the thing is, superintelligence is like saying there's some kind of faster than light information transfer way of doing stuff. Whereas actually what we mean is faster intelligence. And when everyone is used superintelligence, they mean, they can outthink and outdo. If you look at that carefully, that's not super, that's just faster. And we do lots of things faster, right? AlphaGo Zero beat, the best player in the world, but because they had infinite compute power, lots of energy dissipated. But if it was a like for like site, it wouldn't be as the system did not do anything the human didn't do because the humans built it. And so what I'm trying to say is to say, hey guys, when we talk about superintelligence, what is it we mean? Do we mean that faster information processing? Totally buy that's possible. Do we mean kind of access to data that we won't have access to with new sensors? Totally buy that's possible. But do we mean breaking the laws of physics and coming up with a new ontology? That's not possible. And that's what Nick kind of puts into everyone's minds as a little mind worm, which I think if you listen to David Deutsch, and I think David Deutsch is probably the greatest living philosopher right now of physics, he would explain very elegantly, much better than I can, that why superintelligence is just nonsensical from a very good epistemic point of view.
I was actually going to ask you, because a lot of your claims I noticed do dovetail a lot with David Deutsch's AI claims. So in your mind, David Deutsch is basically right on all his AI claims.
I mean, right, I don't know all these claims. This makes sense to me. And so this is where we go into AI science, right? Because lots of you want to do AI science. Here's a worry. But people just basically collect data and compress the data down and infer something. For me, science requires an idea, a leap, and to generate a kind of, and by trial and error, actually, the selection will give you. And then when you got that idea, you then mechanistically work that out and then work out how to do an experiment and collect data. So I have an idea, I do an experiment, I collect data, and then if I use my AI, that's great, because it just helps me get the data. What I see right now is lots of people are skipping the idea and the abstraction and the framework, and they're just randomly getting stuff and compressing it down. And that is not science. And so I think that David and I agree on that. We agree on superintelligence. But I mean, there are some things that David thinks about the multiverse I don't think are right, because my conception of time and David's are different. But I think he's very thoughtful. It's very interesting. I've been doing a lot of thinking. I'm just a chemist, right? It burns stuff and makes stuff. So I'm no guru on this. But what I've tried to do is just say, hey, what do you mean by superintelligence? Let's unpack it. If you mean it's just a faster computer, then great. That's not superintelligence. That's just a faster computer.
Yeah, I'll give you my response to that, which is like, yes, there is a difference of just degree if you zoom out far enough. So if you zoom out far enough, when we talk about intelligence, yeah, we're talking about vast search spaces where, yes, if you could crunch through every single element of the search space, if you had enough time, then you could have a dumb algorithm solve it. But the problem is the dumb algorithm needs to run like 10 to the power of 1,000 steps, right? Like way longer than there's ever going to be time steps in the physical universe. So you need a shortcut. And then the caliber of the intelligence, the IQ, is basically how good the shortcut it always comes up with is. Like, that's basically what intelligence means.
To the heart of our difference, which is really cool. So you think there's a search space, and I think that the human beings create and collapse search spaces all the time. And some of those search spaces, until they're created, aren't searchable. And there's a thing that we go through yet. We don't understand the physics of this. It's not yet done. I'm close to it with Sarah Walker. That's you, but it's not done. And it's something that is exciting for us. And we could be wrong, right? It's okay. But I think that the cracking the origin of life, I mean, I would say it's in such a broken record. The problem of the origin of life is similar to the problem of the emergence of intelligence and consciousness. Understanding all of that will get together. And I think that I love what people have done in AI. I love what people have done. I'm not a fan of Jeffrey Hinton just basically having his God complex. But now he's got a Nobel Prize. Maybe he's right. Maybe he invented the AI. The AI is like, screw you. I'm going to see if I can give my creator the Nobel Prize. And that's proof of AGI.
Right. I guess I do want to throw in one last question for you. If you can think back to your mental state around, let's say, 2019, have you been surprised by the outputs AI is able to deliver these days? Like, would you have predicted in 2019 that there was a decent chance that AI can be writing these thoughtful essays, right? Responding, like, give it a giant paragraph of text, it can, like, analyze, the quality of your argument, like all of these things AI is doing, or like the image generation, right? Like generating a picture that meets your requirements. Like, is this surprising to you?
No, it hasn't been surprising since I was 12 years old. When I was 12 years old, I used to obsess in my backyard. You get the pavement cracks and get tracing paper, and I'd trace the cracks. And I'd try to minimize I'd take the rough trajectory of the crack, and I'd literally try and come up with algorithms that would compress that crack down and allow me to get there. And for me, it's always been very visceral that we were going to do this. And it's incredible that we've been able to do it. Am I surprised? So I guess I'm surprised by the engineering feat that it is. The fact that it works so well, I think is somewhat surprising. In the fact that we went through this big leap in technology, it's almost like we went from just about flying with the Wright brothers in the air and saying that flight was possible. We're just going a lot further, a lot faster. So from that point of view, I guess if I look back, I can be surprised, but no, I wasn't very surprised at all. When Gary Marker saying ChatGPT, so I was like, what's that again? I was like, oh, okay, that's cool now. So it's now useful enough to use. Cool, I'll use it.
The reason I ask is because, like, today, when I ask you to draw the boundary of what AI can do, you give me answers like, hey, in 100 years, that last 10% of drawing a great picture or writing a great song, that last 10%, AI still won't be able to do it. And I can't help suspecting that if we were to go back to 2019, and I asked you to draw the boundary to sort problems into things AI can do by 2024 and things AI can't do by 2024. Yeah, I just feel like you'd probably draw the line in a different place. You wouldn't be like, yes, by 2024, 90% of image generation to spec will be solved,
No, I think it's about different kinds. So I think that what we need to do in 100 years, if you take an AI right now with no developments, right? Or just kind of what we have technologically, without understanding what intelligence is and how the brain works, we're not going to make this. In 100 years' time, will we have artificial consciousnesses in chemical brains somehow fabricated? Probably possible. Is it a 100-year or 500-year problem? I don't know. Depends if we solve origin of life, I guess. So what I'm saying right now, if I extrapolate the current semiconductor revolution and we're just cranking and just building more models and tweaking, no, nothing different is going to happen because the data, the cost of compressing the data, human minds are able to build abstractions that don't exist in the current. And when you say, the quality of the argument, there is no argument. It is fake. All that AI is doing is reading other arguments that other people have made and presenting it back to you in a way that you don't notice. And that we will get to that is what we'll see. And actually it will become quite stale quite quickly. I see students writing AI essays and bullet points. I'm just like, oh my God, whoever put the bullet point thing into ChatGPT, right? I used to use bullet points to describe things, not anymore, because I almost just bullet pointed something out, right?
Right.
But I think misses the point. I think the thing where I've got the most out of AI tools is where I put a lot of thought into generating the stuff I put into it, and then use the corpus of human knowledge to correct it or help it enhance it. From that point of view, AI is an amazing tool, and I wasn't quite expecting for that shift, but it's within the existing category. It's not elite. We need to go to a different kind of technology, and I don't know where that's going to come from. But it's exciting that we're discussing it, we're thinking about it. I think there's a lot more to happen, and it's been a fun chat.
Yeah, absolutely. It's been great to hear your worldview. Now, to wrap these things up, I never go in with the hope that I'm actually going to change the other person's mind just because I'd be continuously disappointed. But my hope for these conversations is to illuminate for the audience and for each other what the other person's view is, because views can be very subtle. So to recap, what I think I've learned about your view and the crux of disagreement between your view and my view is you're coming at it from an interesting position. I would call it an early stop on the doom train. I often talk about the doom train where you get to the end of the train and you conclude that we're doomed. And at the beginning of the train, you have to first get through assumptions like, hey, there's going to be super intelligence. It's going to be better at pretty much everything than humans. So you seem to be getting off at a very early stop on the doom train where you don't even think that an algorithm could be as creative as humans today. And you're not expecting to ever see super intelligence, and you have a lot of the same views as David Deutsch. So today I've learned that you get off on such an early stop on the doom train that the normal concerns people talk about, like once you have super intelligence, it's going to be power seeking, it's going to manipulate humans. Those things just aren't concerns because you've just gotten off on the first steps where it's just not even going to be that creative in the first place. Fair?
Yeah, absolutely. But I think
Cool.
we've thought about a lot of other things. Like hopefully the nuance of my interpretations of things and what we agree on far more than we disagree on.
The other thing I learned about your perspective that was a little bit surprising is you're connecting a lot of things together that I don't think are standard to connect together. So in particular, you're saying like solving the problem of the origin of life on Earth is going to give us insight about how the brain is intelligent, right?
Yeah, absolutely. Something life is doing about mining the future is what we're doing right now, and the mystery. That's the kind of sole purpose of my kind of life, if you like, is to find out what that mystery is.
Cool. All right. Noble purpose. And once again, huge respect for coming on and debating. That definitely puts you in rarefied air that you were brave enough to come into what I like to call the lion's den. So thanks again. It's been great chatting with you.
Really nice to take part. I had fun.
And for you, the viewers, I'll see you back here on the next episode of Doom Debates.